Thanks for attending this session. I'm going to talk about the new language mod that we are adding to Clang that allows you to use C++ in OpenCL mode. And I'm also going to talk about how we try to generalize the functionality as much as possible that it will allow eventually to use C++ for accelerator devices. Let's start from the outline. I'm going to first briefly introduce the concept of OpenCL so that you can follow the rest of the talk. And I'm going to start from describing C++ for OpenCL just conceptually. And the majority of this presentation, I will actually focus on how we implement various features in Clang. And at the end, I would like to talk about generalization to C++, and I will conclude with some summary and future work as well. Let's get started. So what is OpenCL? OpenCL is a programming model that allows to offload computations to accelerators, and it is standardized by Kronos Group. Originally, it's intended for GPUs, but this day it evolves towards supporting various different hardware. For example, you can run OpenCL on DSPs, on FPGAs, custom accelerators, and CPUs as well. So just to explain a little bit more about the model, drawing comparison to C and C++ programming. Typically in sequential C and C++ programming, you will have some hotspots in your application, and that's where majority of execution time is spent. And most of the time, these hotspots will be loops. What you can do with these hotspots in OpenCL, you can just use special API calls to say, now these hotspots are going to be sent for executing in a more compute-capable device. So the application, the original application will still run in CPU, and it is called host in OpenCL terminology. And what you are going to send to a more compute-capable device to execute faster, it's going to be called device side. And it will be compiled with a separate compiler and run on accelerator. Now, this device side is programmed using C99-based dialect, and it actually just adds very few extra constructs to C99 so that the behavior to run on accelerators to be described. Now let's talk about C++ for OpenCL. These days, applications that are run on accelerators are more and more complex, and we would like to have features from C++. So in this work, we are combining OpenCL features such as use of kernels, address spaces, and special types with C++ 17 features. Classes, type deduction, templates, inheritance, all those things. This mode can be enabled in Clang by passing CL C++ std flag, and it allows you to do something like shown here. You can use a template function, and you can instantiate this template function in your kernel, and it will allow you to use the same template function with different data types. Just to clarify and avoid confusions, this is not implementing OpenCL C++ from the Kronos registry. Let's look at implementation in Clang in more details. So first of all, we had to extend driver to support new values for std and CLSTD flag. We also had to add new language mode, obviously, and we had to provide support for all OpenCL special types. They're actually opaque-like types with a few exceptions and a few kind of extra bits you can do with them. So the majority of time, we just had to move the functionality from OpenCL C and be able to share it with C++ paths. We also had to enable all of the built-in functions from the standard header to work in this new mode, and all the Kronos standard extensions are also available and enabled. There are a number of restrictions to C++ feature we had to add, however, and that's mainly because of the way accelerators are some of the features are not easy to support on such hardware accelerators, so we had to disallow things like virtual function and exceptions, and dynamic cast operator, and standard libraries aren't supported either. The majority of work were spent in defining and implementing behavior for interplay of OpenCL features and C++ features. I'm going to talk a little bit more about them. So the first thing is kernel function. Kernel function is an interface between host and device, and what it allows you to do, it is basically just an entry point to executing on an accelerator. There is such an API call in OpenCL standard, CL create kernel, where you have to pass the name of a kernel that will be executed on device. And what the implications are is that the name of a kernel in the device compilation mode has to be kept as is, so it can be mangled. Therefore, we can't allow features like overloading of kernel function or use of this function in templates, or the kernel function can be a member function. This can be simply done by adding C linkage early in parsing, and that's what we did, and we inherited the rest of functionality pretty much for free, apart from we had to change a number of diagnostics just to make sure we are reporting something about specifically kernel function and a generic function behavior. The other feature, that's where we actually spend most of the time, implementing address spaces in C++ logic. I'm going to spend a little bit more time explaining how the things were implemented, or explaining a number of things. But before I actually talk about it, I would like to introduce address spaces in language in general. Address spaces can be, or objects can be allocated to address spaces or memory segments using this special attribute. In this example, variable I will be in memory segment 1, and we can also use address spaces with pointers that basically says that pointer, in this example, will be point to object in memory segment 1. Address spaces are part of type qualifier. And originally, the original specification comes from embedded C. In OpenCL, we extended what has been originally defined in embedded C, and it's mainly to support OpenCL-specific memory model and several other things. I personally find address spaces special qualifiers, and one of the reasons is you can think of casting away address space because you can't remove memory segment from object, or you can't just say that object suddenly isn't in that memory. In OpenCL, we have 5 address spaces, and 4 of them are physical address spaces, and the last one is logical address space. I'm going to introduce it a little bit more in just a few minutes from now. But before I do that, let's just compare address spaces between C and C++ languages. In C99 spec, word qualifier occurs 90 times, and if we are talking about address space qualifier specifically, it will affect the following areas. For example, type qualifier inference, conversions, and casts. Overloading rule, simply because in C we have overloadable attribute that can be used to overload function in C, and also generation into IR. There are 207 occurrences of word qualifier in C++17 spec, and that says for itself. There are a lot more language rules that are interfering with type qualifiers in general. And as for address spaces, we had to look at areas like cast operator, references, templates, type deduction, overloading in general, implicit object parameters, built-in operators, and several other areas as well. Due to time constraint, I can't talk about all of those, but I would like to introduce one of the most relevant and representative problems with address spaces in C++. In C++, we have abstractions, and they are specialized at some point. And that's really great because it allows us to write more maintainable and readable code. Example of such abstraction is classes and objects. Let's look how this concept interplay with memory segments. In OpenCL, if we would like to declare a global variable in global memory, we will write global my class and then name of a class, of an object, sorry. We can also declare this class in local address space. And then we obviously can use methods of both classes. When we are calling a method of a class, what implicitly happens is that we are going to pass an object into this method. And the reason why we need to pass the object that we would like to access to data member of this specific object inside the class, inside the method. What does it mean in segmented memory architecture? Well, every pointer has to point to some memory segment. And if we are declaring a class in multiple address spaces, what this memory segment has to be. There are a number of complications and considerations here. First of all, class definition is parsed ahead of object instantiation. And it is also very common that member functions are defined in completely separate translation module to where we instantiate objects. So what we could do in OpenCL, obviously, we can just duplicate methods for every address space. Obviously, it's not ideal because it will result on large binary size and obviously longer compilation time. It's not something desirable, but it is at least doable in OpenCL. And if we are looking generically at C++, where address spaces are actually arbitrarily specified in the source using an attribute, we can't even know ahead of compilation what address spaces objects are going to be created. And it's actually not something we can replicate member functions at all. So how do we solve this problem in OpenCL? In OpenCL, we have, as I mentioned, logical generic address space, and it's really helpful. This address space appeared in standard 2.0, but these days, most of vendors support this standard. So in this example, we again have global and local variable, and we have a pointer. We don't specify an address space on this pointer, and what it implicitly means that this pointer will be generic pointer. We can assign an address to local or global objects to this pointer. That's absolutely valid in OpenCL. And what it actually means that the resolution of concrete memory segment has to happen dynamically. And we have to have either specialized hardware to do that, or we have to do some compiler tricks when we lower this program into machine instructions to be able to support this functionality. In OpenCL, we are going to use generic address space for the abstractions in C++. One complication here is they have constant address space that isn't convertible to or from generic. Let's look at our example again. And here we have definition of our class. And when we declare a member function, what it implicitly means that we will have generic address space my class pointer passed into it. We don't have default constructor in this case, so it will be added implicitly, and the object parameter will again be in generic address space. On the line 4, we have copy constructor, and because we don't specify an address space, it will be using generic address space both for the object parameter and for the parameter we are copying from. On the line 5, we have copy constructor, and we have added address space method qualifier local. And what it actually allows us to do, it will alter the pointer type of an object parameter and say it is local address space my class pointer. For the second parameter, it will stay the same because we don't provide an address space of parameter for the class we are copying from. Now, if we are creating a variable in global address space, C1, it will use default constructor because we don't actually pass any parameters. And it will have to cast from global address space into generic address space. before it passes allocation C1 into the constructor. On the line 9, instead, we are declaring local address space variable, and we are passing object C1, so we will use the copy constructor. We will use copy constructor from the line 5 because that's the most matching constructor considering address space in this case. And therefore, we will avoid an address space cast from local to generic because we actually have local address space object parameter in this case. For the second parameter, where we are passing an object we are copying from, it will be just exactly the same as object parameter on line 7. So we will have to address space cast from global to generic because second parameter of copy constructor on line 5 is generic address space. Remember, I mentioned that constant isn't cast to generic, and therefore, for the constant address space methods or methods that are to be used with constant address space object, we will always have to provide extra overload in the source code. Let's briefly look at support of global constructor and destructors. Global variables in OpenCL can be used among kernels, and therefore we can just initialize and destroy them at the boundary of kernel execution. For the constructor, it's not too complicated, however, because standard C++ ABI will generate an initialization stub function that we can simply turn into a kernel function, and it can be invoked from the host side just before the execution of kernels. But the destructor situation is more complicated because standard C++ ABI will just register destructor callbacks, and the objects to be destroyed will be passed as parameters. Now, first of all, in OpenCL, callbacks between host and device are really tricky to implement. And second, we can have program scope variables in various address spaces, including constant. So we can't actually use generic address space as a trick here anymore. That's something that requires a big ABI change, and it's something we are going to do in the near future. Currently, it's not supported. Right, so now that I briefly explained various implementation details for C++ for OpenCL, I'm going to talk a little bit also how we try to generalize this to just support C++ on accelerators. If you look at accelerators, they have a number of common features. Memory segments is one of them. A lot of accelerators support vector and SIMD type of operations, and a lot of them are actually parallel, so they provide certain mean of parallel execution. So when we implemented OpenCL functionality in C++ mode, we actually tried to generalize logic as much as possible. And whenever there was something that doesn't actually require OpenCL check and OpenCL specific behavior, we would implement it just as general C++ feature. Here is one example. If we are adding overload candidate for constructors, in this case, we are going to check whether the address space of constructor we are evaluating is compatible with address space of what is requested in candidate set. And that is actually taken from where the object is constructed. If the constructor isn't compatible, or if address space of constructor isn't compatible, we will mark the candidate as not viable and also record why it happened. So we will actually specify that address space is not matching. Here is an example of OpenCL specific behavior. I mentioned that the solution for adding implicitly object parameter requires OpenCL specific functionality and support of generic address space. Therefore, when we add this generic address space into the qualifiers of argument type for the constructors, we will have to check for the OpenCL language mode. Now, the implementation for C++ even involve it does provide a lot of features right now. It's still incomplete, and there are a number of OpenCL-specific functionality that was added that we have to generalize in order to have fully functional support for address spaces in C++. Right, that brings me to the conclusion. First of all, C++ for OpenCL was enabled in Clang 9, and the main features of this language mod is that it's backwards compatible mostly with OpenCL C, and we are allowing nearly all C++ features. There are very few things that we disallow. One of the objectives of this language mod was trying to reuse as much of Clang infrastructure as possible and avoiding very big architectural changes. That's simply because Clang code base is really complex, and there are so many language mods that it supports. It's really difficult to perform large architectural changes. It is an experimental phase, and there are a lot of bugs and maybe even small missing features, and you can refer to this page listed here to see the status of implementation. Obviously, we generalized a lot of logic specifically for address spaces just to work in C++. And we started documentation for this language mod as well. It can be found on the Kronos GitHub repository. As a future work, we will be focusing on completing OpenCL-specific part first, and it's to be compiled and used with OpenCL 2 compatible drivers without a modification. We can simply compile into SPIR-V intermediate format and load in OpenCL 2 compatible drivers. However, in the future, we plan to have modification to the drivers, and that's mainly to avoid some manual steps that will have to be done now, specifically for global constructor and destructor handling. We would also like to finalize generalization to C++ as much as possible, and we will first require completing the concept and then looking at documentation and implementation in parallel as well. And at the end, we are still not very good with testing. There are a lot of things that are really not very well tested, but it's something we would like to do in the near future as well. As a conclusion, I would like to say that this project was a very good example of community work, and I would like to thank John McCall for invaluable feedback and reviews. I would like to thank David Rohr, who started using this language mod very early after we committed just a few patches, and who helped us with testing quite a lot and submitted a lot of bugs. Also, the application that he used was very motivating for us. I would also like to thank OpenCL Working Group for supporting this idea and also hosting the documentation for this language mod. I have one extra slide, and that's for offline reading, actually, but there are very few details I could explain due to time limitation. And if you're interested, you can look up, here are some key fabricator reviews listed. And if you're interested to help, we still have some open reviews, particularly where we are generalizing logic to C++. If you're interested to help and contribute, then we will be happy to have your contribution. Thanks. And are there any questions?
If you have any questions, I could ask that you could come up to the mic.
Just a quick question. You mentioned that this language that you're calling C++ for OpenCL is not the same as the Kronos OpenCL C++. Could you explain a little bit what the differences are and what's the motivation for having these two different flavors?
Yeah, so there are actually several things, and I think one of the biggest thing was backwards compatibility with C. In OpenCL C++, a lot of key features of OpenCL kernel language were just completely changed. The way the address spaces are being used, for example, instead of having qualifiers, you had to use special classes and things like that. And one of the problems with changing significantly kernel language is that if you talk to developers for GPUs, they are not very happy and not very keen to change their kernel code very much. They are okay to change host code. That's completely fine. But simply because debugging on GPU is so complicated in accelerators, once we write kernels and they are functionally correct, we would like not to do too many changes. So backwards compatibility, one of the things we discovered was preventing OpenCL C++ to be adopted, and a lot of developers were just not as keen. But there were also several other reasons, specifically about language, semantic, and a lot of things are defined as libraries in OpenCL C++, and we were missing a little bit on the language definition side to implement it in Clang.
So you mentioned that casting of memory space qualifiers obviously doesn't always work the same way as traditional qualifiers, but there is a pretty reasonable context in which it does, and that's in hierarchical memory qualifiers, right? Is there any work in that direction? And are the things that you wrote for this reasonably compatible with an extension in that direction?
Obviously, we do allow casting between address spaces. For example, in OpenCL, you can cast this logical generic address space to many other address spaces.
Right, of course.
We do support it. What I just find kind of different is in C++, you can cast away qualifier, right? You can remove const. And in kind of OpenCL or segmented memory context, it's kind of, you don't actually remove it, you just place a different qualifier. So address space qualifier will always be there. There will always be an identification of what memory segment the object belongs to. It's just kind of, you can cast between them, but you can't actually cast away address space qualifier.
Okay.
And if there are no further questions, I'd like to thank the speaker.